Okay guys, so this is part 2 of topic 3 on axial load, and we're going to go ahead and continue the discussion and talk about the principle of superposition. So the principle of superposition is something we use a lot in structural analysis, and we're going to start learning about it. Actually, you've already started learning about it in statics, but we're going to continue that discussion for mechanics of materials. So before we get into this, I want to show you guys kind of a very simple idea of the principle of superposition. So let's say we have a system here and we have two loadings on the system. I'm going to call this F1 and F2. What the principle of superposition says is that this system is equal to two systems added together that just has the first load on it in the same location and the second load on it in whatever location the second one was in. And this is really just a simple definition of the principle of superposition. The reason that we use this is because it allows us to break up really complicated loadings into very simple complicated loadings. And just like we added forces here, we can also add displacements, which also really simplifies these complicated systems. We have some conditions when we're using the principle of superposition, and that is that our systems have to be linear elastic. We can't have any massive changes in geometry, and for the purposes of structural analysis or for the purposes of engineering, we really don't have any large geometry changes or any large deformations. We're dealing with very small deformations. So for this class, we will only consider criteria where this is met, where this has been met. Okay. And this is here another illustrative example of what the principle of superposition looks like. So you have, and this is actually in terms of displacement. So you have a system here that's being displaced by some amount, and we can separate that and add it up by two less complicated loading systems. Okay. So statically indeterminate members. So before we get into this, I want to talk about what a statically indeterminate member is. So let's say we have some kind of system. Let's say this is a beam. And let's say on this beam we have a pin, and we have a roller, and we have another roller, okay? And we have whatever kind of loading on this system. So if we were to calculate or count how many unknowns we have 1, 2, 3, 4 unknowns, right? But this is a 2D system. So how many equations of equilibrium do we have? We have sum of moments, we have sum of forces in the x, we have sum of forces in the y. So we only have 3 equations of equilibrium. So whenever our number of unknowns is greater than our number of equations of equilibrium, this is equal to a statically indeterminate system. That's the general definition. Now, we're specifically talking about a statically indeterminate axially loaded member. So we're going to kind of expand on this and talk just about axial loaded members now. So let me go ahead and draw an example of an axially loaded member. Okay. And let's say I have some internal force P applied at some point C. This is point A, this is point B. And we have some lengths that are given here. So we have LAC, LCB. Okay. Now what happens here is this is also indeterminate. Why? Well, because I have these two reactions here. I would have some reaction and some reaction, whichever direction here. So if I were to sum forces in the y direction, I would basically get FB plus FA minus P equals 0. And that's not enough equations to solve for this. So again, for this system, I only have one equation to use. I only have sum of forces in the x because I can't sum moments. Everything goes along the axis of rotation. And I can't sum forces in the x direction because I don't have any forces in the x direction. So this is also a statically indeterminate system. Okay. So what I want to do here is I want to figure out a way I can solve for this. So one method of solving for statically indeterminate systems is to get another equation by relating force and displacement. Okay, I want to build another equation for me to use by relating the concepts of force and displacement. Okay, so I want you guys to think about this for a second. How can I relate force and displacement of an axially loaded member? So I'm hoping you guys watched the first video I posted before you're watching this one, because this will make a lot more sense. But I basically need to use that function delta is equal to PL over AE. I'm going to kind of put it on the side for now, okay? And I also want to show you guys that delta of A, so A is a fixed support, B is a fixed support. So wouldn't that mean that the delta, the displacement of A relative to B, okay, that is basically equal to 0 here, right? That's equal to 0. Neither of those sides can move. Okay. Any equation that we use, by the way, any extra equation like this that we use that basically relates force and displacement, we call this a compatibility equation. Okay. And for this case, again, it is that delta A with respect to B is 0. Now, this is not always the case. You will have to look at the problem you're given and decide what the compatibility is for that given problem. Okay, so this takes a little bit of thought per problem. Now that we know that delta A with respect to B is 0, there's no change, right? It just basically tells us that the force at A, length of AC, over AE has to be equal to the force at B, length of CB, divided by AE, right? And if AE is constant, if it's one material and one cross-sectional area, we can simplify this and we can say that FA is equal to FB times LCB divided by LAC. So do you guys see how we have now built a second equation, and we only have two unknowns. Our unknowns are FB and FA, FB and FA. We know what P is, that's the applied force. We know what the lengths are, and now we have our two equations and two unknowns, and we can solve for what's going on. So we can actually continue and solve and get that FA is equal to P times LCB over L, and FB is equal to P times LAC over L. Okay, so let's now try that in another example. Let's try example 3 and see if we can use this compatibility idea or concept to solve what's going on here. So we have a steel rod that's shown here, and the steel rod is fixed to the wall at point A. And before it's loaded, there's a gap of 0.2 millimeters between the wall at B prime and the rod. So we have this little gap here before loading. Okay. We want to know what the reactions at A and B prime are if the rod is subjected to an axial force as shown. And basically we're given the modulus of elasticity of the system and the area, everything we need to solve for what's going on. Okay, so we're going to first start this problem by assuming that this force P is going to be large enough to cause B to touch the wall. So we're going to assume that B touches the wall. It basically fills the gap. Okay? And this system is statically indeterminate because I have these reactions at B prime and A prime. So I have two unknowns. But the only equation that applies here is sum of forces in the x because I don't have moment and I don't have y. So this is statically indeterminate. Which means I need a compatibility equation. Okay. So let me start here. Let's start by actually getting our first equilibrium equation. So sum of forces in the x is equal to 0. This direction is positive. I have negative FA. Oh, I'm going to draw my FA here. Negative FA minus FB plus 20,000 equals 0. This is one equation. I need another one though, right? So compatibility now. Right? I know that the displacement of point A relative to point B, point B relative to point A. I know that the displacement of B relative to A has to be 0.0002 meters, right? I know that it has to be this 0.2 millimeters. That's how much that point has basically to move. So if that's the case, then I can say that delta B with respect to A is 0.0002, which is just equal to the difference, right? The force at A, LAC, divided by AE, minus the force at B, LCB, divided by AE. The difference between those two displacements has to be 0.0002 relative to A. So now I need to figure out what the internal forces FA and FB. So to find FA, I'm going to make a cut. Right? And I'm basically looking for this FB as well. And now I'm going to plug everything in here. So I get 0.0002 equals FA times 0.4 divided by pi times 0.005 squared times 200 times 10 to the 9 minus FB times 0.8 divided by pi times 0.005 squared times 200 times 10 to the 9. And I simplify this, I get FA times 0.4 minus FB times 0.8 equals 3141.59. And this is my second equation. to come here and highlight. So I have this equation, I have this equation, I have two equations and two unknowns, and I can easily solve for these now using algebra, and I get 16 kilonewtons and 4.05, which is really just 4 off by a little bit due to just mathematical rounding. And those both equal 20, which is my initial applied load. So everything makes sense. Okay, let's try another example here. So in this example here, I have 3 steel bars that are pin connected to a rigid member. So remember what rigid means. It means it's a stiff member. It does not deform. Okay, so only the steel bars are going to deform. If we have a 15 kilonewton load applied, we want to determine the force developed in each bar. The bars have a cross-sectional area that's given, and so do the other ones. So what we want to figure out is what is the force developed in each bar in this system. Okay, so the reason this is statically indeterminate is because if I want to draw my FBD here of the bar, what I end up getting is I get this 15 kilonewton load, and then I have F, what did I just call this? FA, FC, FE. So I have 3 unknowns, and I only have 2 equations. Why do I have 2 equations? Because for equilibrium, I can sum moments about a point and I can sum forces in the y. So let's sum moment about point C. I get negative FA times 0.4 plus 15 times 0.2 plus FE. And then I can sum forces in the y. I get FA plus FC plus FE equals 15. So I have 1 equation, 2 equation, 3 unknowns. I need to now go to compatibility and develop a 3rd equation. Okay, so how can I use compatibility to figure out what's going on here? So basically what I can do is I can relate my displacements at E, C, and A using similar triangles. So here I have the rigid bar, and I know that point A is going to move down by some displacement, and I know that point E is going to move down by some displacement, but E is going to move less because the 15 is closer to point A. And then I know that that's a rigid bar, so it's not going to deform, right? And what I want here is I want the force in each system, but now I can use these triangles to relate what's going on. So this here is delta E. This here is delta A. And this here is delta C. And this little portion here is delta C minus delta E. And this portion here is delta A minus delta E. So if you guys see from these triangles, I get that delta A minus delta E is to 0.8, as delta C minus delta E is to 0.4. And I can solve, and I get delta C is 1/2 delta A plus 1/2 delta E. And how did I get that? I just cross multiplied and solved there. Okay. Now what I can do is I can plug in my equation for delta. So delta C is FC LC divided by 30 E of steel, which is equal to 1/2 FA L, all the L's are the same, 50 times E plus 1/2 FE LE divided by 50 EST. And I end up crossing out all of the L's, all of the E's, and I end up getting here FC is 0.3 FA plus 0.3 FE, and this is now my second equation. So I have this equation here. I'm sorry, that's my third equation. What am I doing? I have this equation, and this equation, and I can solve for all three now. I get FA is 9.52, FB is 3.46, and FC is 2.02. Okay, so we're going to stop here for this video, and in the next video, we're going to talk about thermal expansion and contraction.